In the last class, we were discussing this palladium catalyzed coupling reaction, famously known as Buchwald-Hartwig coupling. This reaction deals with formation of a amine. So if you start from a primary amine, you will get a secondary amine. If you start from a secondary amine, you will get a tertiary amine. And the organic halide is involved in these cases, usually aryl halide. It could be aryl chloride, bromide, iodide, or triplet, or many other variations of it. Okay, so whenever you have a aromatic ring, you have an aromatic ring. Outside that aromatic ring, if there is a nitrogen bond, for example, over here, as you can see, this is the nitrogen outside this benzene ring. Okay, if you look at this molecule, this nitrogen is there as well as this nitrogen is there. Whenever there is a carbon nitrogen bond formation outside the benzene ring, this is the reaction that you try to follow. Okay, that's what we have discussed in the last class. What we are having essentially is an aryl iodide, for example, over here, and a nitrogen coming and doing the reaction at this center. Okay, so to speak, if you have aryl halide, such as it is written here, so benzene ring and X, like bromobenzene, for example, okay, or chlorobenzene or iodobenzene, such as these aryl halides, if you take and you take simple amine such as aniline, then you can form a new, so this is your starting aniline, you can form a new carbon nitrogen bond. Okay, so this is the Buchwald-Hartwig coupling, right? So what happens with the starting material? Starting material, that is aryl halide, undergo oxidative addition with palladium 0. Palladium is in 0 oxidation state to give you palladium 2 plus aryl halide oxidative addition intermediate. Right now, depending on the nucleophile, that is over here amine, you can see different steps where essentially you see the aryl group and nucleophile come very close, which is held by the palladium metal. Overall, then a reductive elimination, that means bond formation between aryl group and nucleophile takes place to give you aryl nucleophile. That means this product formation happens. So by utilizing this method, we have seen yesterday that we can synthesize many important organic molecules. Wherever, let's say, there are many molecules, many medicine, many materials, many compounds that is there, where you will see carbon nitrogen bond formation, right? This carbon nitrogen bond formation can be done by this carbon nitrogen bond formation process or palladium catalyzed carbon nitrogen bond formation processes. You can have application in process chemistry, medicinal chemistry, material science, different ligand synthesis, synthesis of natural products, as well as synthesis of heterocycles. Many domain, many different domain, wherever you have a carbon and nitrogen bond formation right outside a benzene ring, this is the method of choice. All these molecules are very important ones. As you can see, the highlighted one, the bond highlighted in red here, are the ones which can be generated by this method. So this bond, this bond, this bond, all of these are generated by this palladium catalyzed carbon nitrogen bond formation reaction. Any reaction condition you see, the yields are good, temperature is not that bad, you need a base, you need a phosphine ligand, as well as you need a palladium catalyst. Overall, each of these compounds are very important pharmaceuticals or agrochemicals or industrially relevant molecule which can be assembled together if you have this molecule, if you have this method available. Here are some more examples. For example, you can take these sort of very difficult to react amine, okay, amine with different heteroatom in it, and then take an aryl halide. You can do this carbon nitrogen bond formation. This bond formation is done by this method. Okay, as you can see in all the cases, say for example this bond, this carbon nitrogen bond, this carbon nitrogen bond formation is done by this Buchwald-Hartwig coupling reactions. Okay, now this is nilotinib. I was mentioning yesterday also, this is really a life-saving molecule. It's a pharmaceuticals. This can be synthesized by this method, where once again you have taken a benzene ring with an halide there and a nitrogen nucleophile. Okay, this nucleophile can be added on this electrophile, here aryl bromide, and this new bond can be generated, and subsequently overall transformation will give you nilotinib. Okay, so the bottom line here is, wherever there is a carbon nitrogen bond outside benzene ring, you can essentially synthesize that bond with the help of this sort of coupling reaction. Here in this case, let's say these two bonds can be generated by this Buchwald-Hartwig coupling reaction. Now, so we also discussed in the last class briefly that the problems associated with palladium 2 and palladium 0. Palladium 2 plus is not really the active catalyst. The active catalyst is palladium 0. But this palladium 0 is commercially not too many available, mainly because it is sensitive. Palladium 0 oxidation state ligand complexes are sensitive, very reactive. To provide some sort of stability, these different ligand, such as you see DBA or triphenyl phosphine, all these different ligands are used. But these ligands, since these are good, decent ligands, they don't want to leave palladium. But these ligands are not good for the traditional reaction that we are talking about, let's say cross coupling reaction, right? Palladium catalyzed carbon nitrogen bond formation. So you need an extra ligand L, which is usually very expensive ligand, coming into picture. You don't want this ligand to compete with DBA. What you do, that's why you take very cheap and readily available palladium 2 plus. In situ you generate palladium 0 in the reaction mixture along with ligand. Okay, so you take palladium salts which are very readily available and cheap, you in situ reduce to palladium 0 and you add ligand in the process. What you don't do is you take any of these compound, palladium DBA or palladium tetrachistrophenyl phosphine complex, and then add the ligand, because that this pathway you don't do. That is because this DBA will always compete with this expensive ligand L which you want to add, right? These are the very precious ligand and very important for these transformations. So how you reduce palladium 2 to palladium 0? Why you need to reduce? You need to reduce it because in the reaction palladium 2 cannot really do the reaction. It has to generate palladium 0. the reducing equivalent can come from the reagent. Reagent could be boronic acid, amine or phosphine ligand itself. Okay, what we have seen, for example, in the case of phosphine ligand, okay, in the case of phosphine ligand, which is the very expensive ligand that we want to use, particular ligand that we want to use, that ligand gets oxidized to phosphine oxide. But it's not like all the ligand is getting oxidized, only a little bit of the ligand that we are adding can be oxidized to phosphine oxide, and the palladium 2 can be generating palladium 0, and this is the process by which this palladium 0 ligand complex as well as phosphine oxide are getting generated. So this reaction is happening all the time in the reaction. Under the reaction condition, this reaction must happen. So palladium 0 phosphine compound is always forming under the reaction condition. Okay. Now let's look back at this important reaction. What we are looking at here, is a simple reaction where you take aryl halide, as we have discussed, like ARX. This X could be chloride, bromide, iodide, triplet, you name it, different good living group can be there and an amine to give you a secondary or tertiary amine. If you have a primary amine to start with, you get a secondary amine. If you start with secondary amine, you get a tertiary amine. Now, if you are looking at, these are the different expensive and important and very useful ligand that people use. Okay, these are the ligand popularized by Buchwald. This is the ligand which is popularized by Hartwig. There are many other variations of these sort of ligands, and there are carbene based ligand which is popularized by Nolan, Herman, and these are Verkades ligand, Kwong's ligand, Bellar's ligand. These are different research group who has developed many different types of ligand, right? So one of the questions that comes into picture is which ligand you would like to use for which type of reaction. This is something it required much further detailed discussion. Or let's look at the catalytic cycle one more time. What you have in the mixture, you have in situ generated, you are generating in situ ligand palladium 0. These ligand are those ligand which I have discussed in the last slide. Now palladium 2, like palladium 2 acetate or palladium 2 chloride, is getting reduced to palladium 0, right? This is what it is getting, and this is very, very important for your reaction to happen. If you are not able to generate ligand palladium 0, this reaction will not go forward. Now the oxidative addition into aryl halide, like aryl bromide, like bromobenzene, chlorobenzene, iodobenzene, happens right over here, and you get oxidatively added product. AR group and X is added in here. Now subsequently what happens? The amine binding occurs with the palladium, right? Amine can bind with palladium. So you have a ligand. Usually if you are discussing the monodentate ligand from the last slide, one coordination from the ligand, one coordination from the benzene ring or aryl group, another coordination from X, another coordination from nitrogen. Overall, these HX go out, okay, from here, this H and this X. HX goes out in presence of a base. So let's say HI or HBr or HCl goes out in this step, and you have a metal or palladium, benzene ring, as well as nitrogen. Now this carbon and this nitrogen forms the bond reductive elimination to give you aromatic amines. This is reductive elimination. Once again, very briefly, These are the ligand. Let's say we are trying to take this Buchwald's ligand, which is a monodentate phosphine ligand, very effective for these reactions. And so this ligand that you have seen in there is the ligand in here. If it is a bulky ligand, usually it is one ligand that supports the palladium. It is getting generated by in situ reaction between palladium 2 salt, which is usually palladium acetate or palladium chloride, in presence of the phosphine ligand or any other reducting agent, or reduction happens to give ligand palladium 0 complex. Then oxidative addition into aryl halide gives you oxidative addition complex, where you see AR group is here and X group is here. X group is here. They are undergoing the oxidative addition complex. Okay, amine coordination with the metal centers. HBr or HCl or HI goes out in presence of base to give you aryl nitrogen intermediate on the palladium. Subsequently, carbon nitrogen bond formation takes place between these two to give you aryl amine. Okay, so this is how, once again, you get aryl amine, like aniline derivatives. If you start with an aniline, you get diphenylamine. If you start with phenyl alkylamine, you get diphenyl alkylamine. So primary amine gives you secondary amine gives you tertiary amine. So either primary amine or secondary amine you react with, and this is really an excellent reaction. Not only that, you can react ammonia with bromobenzene so that you can get even aniline, right? This is, even the primary amine synthesis can be possible. Okay, from ammonia and bromobenzene, a similar mechanism should give you aniline synthesis, right? This is wonderful transformation. It works out quite well in the same mechanism as you see in here. So the oxidative addition, amine binding, deprotonation, reductable elimination gives you the product formation. That's really powerful. Now, one of the things we really need to understand, why this sort of ligand designing is required. Okay, what you see here is a phosphorus ligand, two bulky group, cyclohexyl or tertiary butyl, and on there a phenyl ring which is biphenyl, right? So if you look back again, you have a phosphine, and you have two cyclohexyl group. You have, that is kind of, let's say, common here. Depending on that, the name may change. So this is common. These sort of ligands are very good. One phosphorus, and so phosphorus usually have three coordination. So one is cyclohexyl group, another is cyclohexyl group, or these two groups can be tertiary butyl group. And then another is the aromatic, that means over here, this highlighted whole part, right? This is the ligand part with one arm big. So in this case, this is the aromatic part. If you see, there is one motif that is constant, and that is the biphenyl, means two phenyl ring in a way that is constant, right? See, this phenyl ring and this phenyl ring constant, this phenyl ring constant, this phenyl ring constant. Of course, there are different substituent presents on each of these benzene ring, the bottom benzene ring, right? Okay, one thing is, of course, many variation can be there on the top ring as well as the bottom ring, but this biphenyl ring becomes essential for different transformation. Now the thing is, why do you need this sort of drawing or this sort of phosphine ligand? Why It is so good to have these groups. One thing you have to notice or remember that one of the major objective of this sort of transformation or this sort of reaction in industry is to make sure that the palladium loading is very little, because that is going to be very crucial. If the palladium loading is way too high, nobody is going to really use it industrially, because trace amount of palladium maybe that is left on there could be very bad for future studies. Let's say if a medicine is synthesized by using this palladium containing compound, or then we find out that very little amount ppm level of palladium cannot be removed, then nobody really is going to use that product. So for example, if any medicine we are consuming and having, and these are having palladium in it, because the preparation of those medicine requires some process like these, well, this is basically you have to throw it away. Company should not or cannot sell such material where the impurities such as palladium, whatever tiny may be, is still present. Okay, so the tolerance level of such heavy metal which can be having toxic effect in our body is very little. Okay, so that means that the palladium catalyst that is so very crucial and so very important to make this compound should be used in as little amount as possible. Okay, so the palladium we should use very tiny amount. If we are to do that, that means the catalyst loading has to be very less, then the catalyst efficiency must be excellent. Now, how do you make the catalyst efficiency excellent? Of course, you have to find a suitable reaction condition, but more critically for this sort of reaction, it's the ligand, that is the phosphine ligand, that controls the efficiency part. And therefore, the design of the phosphine ligands is absolutely critical for the successful implementation of this reaction in industry. Okay, and that is where we need to understand what is the design factor that comes into picture that makes this sort of ligand so very important. Okay, so this is where we are going to look at why this sort of ligand designing is so critical to improve the efficiency of the reaction. Not only this carbon nitrogen bond formation reaction, for many other reaction including Suzuki reaction, Nigisi reaction, many palladium catalyzed reaction, these phosphine ligands are used. Why they are so good? Why all across the academia and industry people are trying to use this sort of ligand? Okay. Now let us look at the same catalytic cycle with little bit more detail. Okay, as I said, you start with palladium 2 plus. Okay, you start with palladium 2 plus, usually not really palladium 0. You start with palladium 2 plus and you add the ligand. What is this ligand? This is the ligand. The ligand we were showing in the last slide. This is the ligand. It's a bulky ligand, as you can see, quite engineered, very much engineered ligand. Okay, one ligand per palladium. So this phosphine ligand binds palladium, but this phosphine is monodentate, palladium in zero oxidation state. So what would be the electron count for such metal phosphine complexes, palladium phosphine complexes? Palladium 0. That is going to be total 10 electron, and phosphine 1 phosphine 2 electron, 10 plus 2 12 electron. But these species are going to be very unstable, right? As we were discussing, 18 electron species is usually metal complexes try to form, and this is where the bottom ring or this triisopropyl phosphine containing ring in this drawing comes into the picture, which interacts with the metal to stabilize it. So to speak, it gives the 14 electron species. in absence of this dotted line, which now blurred, in absence of this dotted line that you see in here, this dotted line, it was, in absence of that, it was 12 electron, but in presence of that, it is really 14 electron species. That means some sort of stability can be given. So the phosphine binds with palladium on top of this benzene ring. This you cannot call this as strictly a coordination as such, but interaction is there, right? Enough interaction is there. Crystal structure has been known, which shows that there is this interaction between this benzene ring, this benzene ring, as well as this palladium. Of course, palladium is bound with this phosphine. Now then what happens? The oxidative addition happened with aryl, let's say bromide, okay, or chloride in this case, chlorobenzene. So you get pH and Cl from chlorobenzene. So now palladium is having 4 hands. It was having 2 hands to start with. Now palladium having 4 hands. Palladium is 2 plus, right? This is 1 minus, chloride is another minus. Palladium 2 plus is going to be 8 electron system. So 4 ligands, 4 times 2, 8. So this is total 16 electron system, right? It's a 16 electron system. Now it is getting stabilized, but the problem is now this is really a bulky type of system overall here. Palladium 4 coordination, everything is fine, but if the amine has to coordinate in there, amine essentially palladium 2 plus D8 system, that means it's a square planar complex, amine coordination is going to be not that very fast. So as I was telling you, the design of this ligand is such that the efficiency of this catalysis is the highest. Okay, so this is what the ligand designing really kept in mind for. And now that is once that is achieved, and then what it can happen, then there is a free rotation around CP bond, which can rotate around and come outside of this orientation. As you can see over here, it came out. So palladium was on top of this phenyl ring, it came out and outside, and this is when amine binding is happening. Okay, before that, during the oxidative addition stage, amine could not have bound the palladium, right? Subsequently, what has happened, the deprotonation and dechlorination, proton and HCl goes out to give you an orientation where ligand, aryl and NRR prime is there. Then the bond formation between aryl and NRR forms to give you the reductive elimination complex. Okay, let me tell you once more. To start with, for the ligand palladium 0 complex, this palladium is on top of this phenyl ring. During oxidative addition, it is still on top of this phenyl ring. But during amine binding, this crowding is such that this amine cannot bind with the palladium in this orientation. So palladium takes the help of the CP bond rotation. This bond rotates and palladium comes outside or away from this bottom phenyl ring, outside or away from the bottom phenyl ring. Subsequently, the amine binding becomes feasible. As you can see, amine now can bind. Previously in this orientation where palladium is interacting with the bottom phenyl ring, amine cannot bind in this. So amine binding becomes facile. And then HCl removal, H from this amine and Cl from the here, HCl removal gives you an intermediate where palladium is bound with nitrogen and palladium is bound with carbon. Now then the reductive elimination between two reagents happens to give you a higher order amine. Primary amine gives you secondary amine gives you tertiary amine. So this rotation, I think, was very crucial, where palladium from inside it comes outside. Okay. Now during what happens during reductive elimination, it again comes back in, because this is where it gets the crowding. So after this deprotonation, it comes back in, and then it gives you the reductive elimination. Okay, I'll discuss a little bit more in the subsequent slide. So overall, what you are seeing is on palladium is really like on in here, it goes out, again come back in, on off type of situation it is happening. Overall, this on off cycle type of thing helps precisely where help is needed. During the oxidative addition stage, you need the palladium to be on the phenyl ring. So that's fantastic, it is on there. But during amine binding, it cannot be on the phenyl ring, it comes out and binds, and then deprotonation or HCl comes out, right? But at that point, when that happens, at that point, this is not a really good intermediate or good way to undergo reductive elimination. Reductive elimination would require bulk, and then subsequent species generated should be stabilized, and that is why palladium comes back in again. Okay, so again reverse that CP bond for rotation happens. What was happening in here, here it was rotating away, and it comes back in again. Okay, this orientation means that now the palladium is feeling bulky because it has 4 coordination back again, and that's why this goes out together. So not only amine binding and deprotonation, the reductive elimination is also really helped by these processes. Okay, so let's look at this overall orientation in a much clearer view. As you can see in here, what you see a subtle, it's a subtling thing, right? This ligand is acting in a much smarter way than you can imagine. Okay, it is putting the metal or palladium in this case in this very low coordination. Only one ligand is there. There is not like 4 phosphine ligand. Only one phosphine ligand is there. It's a D12. It's a total 12 electron system, which is getting help from the bottom coordination to get some sort of 14 electron system. Because it is lonely alone, it cannot have a, it cannot have an orientation where palladium is not supported. So one phosphine ligand may not give enough support. That's why this dotted line or the interaction from the phenyl ring becomes critical. At this condition, palladium and this ligand is electron rich enough to undergo oxidative addition. So this oxidative addition step, OA, requires electron rich ligand and not too bulky ligand. Okay, small yet electron rich ligand, and that is where the oxidative addition is happening. In this sort of ligand, oxidative addition is never really that much of a problem. So it happens very confidently and efficiently. And from there on, what happens, as I was telling, the amine binding in this palladium is not possible because this palladium is already in 4 coordination mode. Amine binding will not be really feasible in here. What happens? So the CP bond rotation happens. So it has come out, the CP bond rotation has happened, and palladium from inside, as you see over here, from inside or on top of this phenyl ring, it moves away, it swings away, on off, swings away. Okay, and in that condition, amine binding is now possible. Amine binds, and then HCl removes the neutralization with a base. HCl, hydrochloric acid, comes out, and gets neutralized by the base, and now you have a situation where palladium, nitrogen, and carbon from the aryl ring and phosphine is there. Now this was outside, it has to go back in, it comes back in. Why? Because the reductive elimination when it was outside means over here, if it was over here like this orientation after deprotonation and Cl removal, this geometry is not really great for reductive elimination. For reductive elimination, you need bulky ligand. Scaffold has to be bulky, okay? And this is once can be provided once it is come back in, and palladium again feels like many crowded atmosphere is there, and then reductive elimination becomes faster, okay? So palladium was previously, before reductive elimination, it was like this outside. Now it swings back in, and you see the same thing which was outside comes back inside. This orientation gives you very quick reductive elimination. Okay, this gives you very quick reductive elimination. So essentially what you see what we were trying to tell you, that on off, palladium comes in, palladium goes away. Within one ligand, things that is holding palladium, that phosphine ligand, it brings to a certain orientation to make certain things possible. It swings back to make other things possible. Okay, oxidative addition and palladium zero formation and oxidative addition was really in this orientation where palladium is on top of the ring. Now it, during the amine binding as well as deprotonation, you have palladium away from it, but during reductive elimination it comes back in again, right? It comes back in again. Sorry, I have, it comes back in again to give you the reductive elimination. This is like on off, on off, on off with a particular purpose. It's like electric switch on off. It's swinging in and out, in and out. This is happening at a molecular level to promote this catalytic cycle very, very efficiently. And this is so efficient that the palladium loading, the amount of palladium required for the industrial scale carbon nitrogen bond formation becomes very, very little. Okay, so this inherent mechanism, of course, understanding was very, very exciting. This inherent mechanism makes sure that these reactions works quite efficiently. So what we have tried to tell you so far is why this sort of biaryl phosphine ligand systems are so good in palladium catalyzed carbon nitrogen bond formation reaction, as well as many other cross coupling reaction, many other different type of reaction, not only with palladium, with other metals as well. And that is because of the switching the orientation, the way they are flexible, the way they can adopt, just like kind of chameleon, you can say. Depending on the situation, they change their color, right? Depending on the need, they can deliver what is absolutely needed to be done. And by switching these conditions, you have an opportunity to make these reactions very, very efficiently. Okay, I hope this has been exciting. As you can see, palladium is on here, palladium is on here, palladium is out, palladium comes back in, and then forms a product, right? See, at least this amine binding and deprotonation, two step, where here I did not show that. So the palladium is out, away from it. All other stage, palladium is in, and these are with purpose. These are with precious purpose, what is required to be done. So this is what, again, same thing is told in a little bit different way, where you see that oxidative addition, after oxidative addition, the rotation was not really something you would expect to be otherwise happening. There is a need for it. So walking through these slowly. If you see after oxidative addition, this interaction was there, it rotates, it comes out, and a vacant coordination site is there. It is now palladium is in 3 coordinated species. So if you look at 1 2 3 6 electron and palladium 2 plus, so that is 8 plus 6, 14 electron species. Now amine coordination makes it 16 electron species, right? This 16 electron species in a square planar geometry, 4 coordination, it is fantastic. Now the deprotonation and chloride leaves, HCl leaves, that makes it again 8 to 12 electron species. 12 electron species has to come back in, and then it undergoes reductive elimination. Okay, so I hope you have realized how simple ligand modification or design, I would not say these are as simple as it looks like. It took decades of research, it took many hard work, improvisation to come to an understanding what it is really required to make these ligands so effective, to make this system efficient, so that this palladium catalyzed carbon nitrogen bond formation reaction becomes really important in industrial scale, definitely in academia as well. So this is the overall catalytic cycle, as you have seen, compared to other metal catalyzed carbon-carbon or carbon other bond formation. This is the mechanism which is similar to those, and oxidative addition, amine binding, deprotonation, reductive elimination, simple steps that happens. Now a lot of things, as we have started discussing, lot of things that can go wrong. What are the things perhaps that can go wrong, let's say, in industry scale, right? These are, hundreds of kg scale we are talking about. Of course, you need a suitable palladium. As I said, this may not be usually the choice. We take palladium 2, usually palladium acetate or palladium chloride. Now activation of that to this palladium 0 is usually the first hurdle you have to cross. Sometimes this achieving this oxidation state or getting this compound is not happening that very easily, right? So this is a huge trouble. At points this doesn't happen that very easily, therefore reaction may not be going that very easily. So that's the number one problem. Lot of cases, if you do not have the suitable ligand, if you do not have this suitable ligand, then if this ligand is not good, this oxidative addition will not be happening very effectively. Okay, this may also be prevented. Okay, if you are if you are not doing these ligand choice effectively, so this reaction event will not happen. Okay, that is another problem. So lot of cases the X group, as you know, will dictate the rate of the reaction, whether reaction is fast or slow, this X group, right? Traditionally it is found that chloride is the slower one, then bromide, and then iodide is faster. Now with this ligand which we have discussed a moment ago, this oxidative addition is relatively faster. Okay, still of course aryl chloride, bromide, iodide relative reactivity remains, but this is usually a good reaction. Not much trouble happens at the oxidation state. This step is also usually okay, but if you don't choose the right ligand, then any of these steps could be problematic. If any of these steps has problem, you can imagine industry is not going to be able to do the product formation what they are looking for, because the loading, palladium loading will be required too high. Many side reaction will come into picture which they are not interested in dealing with. The yield or the production of the main compound will go down significantly, and this is where you see an aryl halide oxidative addition goes on, which is a fantastic step. This was is going on. Once that is there, then amine binding happens. Okay, amine binding gives you these intermediate, right? This intermediate where amine is bound. Now this is also a critical stage, although usually that this there may not be the problem, but you need to have a suitable amine which works. Lot of cases what could happen that this amine binding step could also be a problem, depending on if you, let's say, have an amine which has other ligand in it, like other heteroatom like nitrogen, oxygen, sulfur containing amine. Now those can effectively bind with the palladium and can make sure that the forward sense reaction is not that going on very well. So overall your system should be sensitive, show that, or robust, so robust that any substituent that is present either in this aryl group, in aryl oxidative addition in this aryl group, or this amine part, any substituent that is present, it should not be able to stop the reaction or retard the reaction very effectively, right? This is a fundamental things to understand, that each and every steps must go on very effectively. Lot of aryl halide may not undergo oxidative addition very effectively. This could be a problem. This is why role of ligand and the reaction condition becomes so very critical. And then amine binding, amine can bind, but then it may not want to come out, or it can take the palladium to a sink, to a process which is unwanted, so the desired reaction may not happen. And then what has happened, that you need the deprotonation. Usually again this may not be the problem if you have a suitable base. Often this sort of reaction, at least at the beginning, earlier stages, you needed strong base. Now that is no longer necessary. You can have weak bases that can still do the job. And of course the demerits of the strong bases is different functional group that is present, different groups that you need in your molecule, which are sensitive groups, may be getting affected if you have a strong base, right? Usually if it is a weak base that is used for this reaction, then it is much better, okay? And that is what now with a good ligand that is actually possible nowadays, okay? Subsequently, you see that this reductive elimination intermediate, prior to reductive elimination you form the intermediate, and as you have seen, the palladium which was outside, it has to come back in for the biphenyl biaryl phosphine ligand based system to give the reductive elimination process. This has, I hope this has been really exciting, and that seeing it on and off, I would say quite exciting. If you have any question, I'm ready to take now. Are you having any question in this process, overall in this process or in this catalytic cycle? The side reaction that can form, I was trying to discuss. Many side reaction can form, as we have discussed also briefly previously. If this reaction or any of these sort of reaction does not go well, two of the aryl group from the aryl halide can give you biaryl or biphenyl, or arene, simple ARH, proto-deboration may happen, right? This proton source could be amine, or it could be any other solvent source, and so on. So diaryl formation could be another problem. Arene, simple arene reduction could be another problem. You can have, if it is mechanisms, depending on the mechanism, amine coupling or diazo formation, or beta hydride elimination from amine if it is an aliphatic amine. There could be many different side reaction that could be happening, okay? To make this reaction happen, each and every steps must be perfect, right? And these things are being made perfect by suitable ligand, as you have seen, this is one of the example which takes care of many problems that one may anticipate for these sort of reactions. Okay, any question you have at this point for me? Okay, if there is not much question, what we can do is we can try to wrap up by saying that these sort of reactions has been extremely useful for promoting these reactions in a way that makes much sense and much useful in the industry setup. Okay, so by utilizing this method, many other side product formation can be prevented, which is what essentially we want to be prevented in many cases. But sometimes it may or may not have happened. But this remains the major groundbreaking way to make the carbon nitrogen bond formation. Just like carbon carbon bond formation, two carbon carbon bond formation, carbon nitrogen bond formation involving, let's say, one of the arene ring, one of the benzene ring, got to be one of the fundamentally most important and widely used reaction. Okay, and this sort of reaction makes sure that things goes on really perfectly, and we have the amine synthesis. Usage of these reactions involve those in industry where many small molecule, let's say pharma industry, right? So there you need to make many molecules, let's say 10,000 molecules very quickly in 5 days you need to prepare. So these are the ways, very rapid screening you can do or preparation you can do by these sort of, let's say, carbon nitrogen bond formation. Many different variations of a potential heat can be generated very quickly, right? These pharma medchem medicinal chemistry studies, it becomes very useful because these can diversify the synthesis as well as structure activity relationship studies in the medchem setup, and this has been really useful for many other applications. Applications are not limited to pharma industry. All different industries can have this sort of application and can be extremely beneficial for the development or the very effective reaction that can be generated from this. Okay, with this, if you have any question, I can try to take right now. If not, we will see tomorrow. Okay, with another topic on these sort of homogeneous catalysis. We might will discuss a little bit more on this, just a little bit how palladium zero is synthesized, pre-catalyst is synthesized. Okay. Any question at this point? If not, we are going to stop today. Okay. Thank you very much. I'm stopping now. Okay.